Success is not the key to happiness. Happiness is the key to success. If you love what you are doing, you will be successful. A very good morning to everyone presented here. Myself, Usharani, Senior Assistant Professor, Department of Mechanical Engineering, Nadimpalli Satyanaraju Institute of Technology, Sundyam, Visakhapatnam. So I take privilege. I welcome you all to all the dignitaries to 1 week online faculty development program on these which is organized by the Department of Mechanical Engineering from 5th June to 9th June. This faculty development program is basically arranged for working professionals, faculty members, research scholars, and MTech students, those who are interested to enhance their technical knowledge and to carry out their research in the recent advancements in mechanical engineering. The speakers of the current faculty development program are working in various reputed institutions like IITs, NITs, and universities. We are also having a few sessions from experts who are working in UK and Ethiopia. We thank all the experts for accepting our invitation and come forward to share their expertise and experience with the faculty members and research scholars out of their hectic schedules. I'm happy to announce that we got hug response, more than 100 registrations across the country like Jammu, Chhattisgarh, Pune, etc. As we informed earlier, we have more than 10 sessions and every day session will start 10 a.m. to 12 p.m. and 2 p.m. to 4 p.m. We will take session-wise attendance and feedback from registration members. For any further information, you may contact us through WhatsApp group. Before concluding my welcome note, I thank NSRIT management and Director Sir for providing the financial support for conducting this 1 week online faculty development program in Department of Mechanical Engineering. I thank Head of the Department and all the coordinates for their efforts and continuous support to make things easy for conduction of the grand event. In this regard, I invite Dr. Vijay Kumar, Professor from Department of Mechanical Engineering, Nadimpalli Satyanaraju Institute of Technology, to welcome the address. Sir. Sir, Vijay Kumar, sir.
Yes, ma'am.
Yes, sir. I'm handing to you, sir.
Hello. Very good morning, all.
Yes, sir, you are audible. Thank you.
Very good morning, audience. So, we thank each and everyone who has enrolled into this FDP program. Madam, is it audible?
Sir, you are audible, sir.
Yeah, thank you. Good morning, one and all. Thank you so much for your interest in attending this FDP. So we are welcome with your So we have a good number of participants. We have lost more than 100 participants, and I'm very thankful to each and everyone for taking the interest and attending this FDP. So as you know, this is a 5 days long FDP, and we have planned sessions, daily 2 sessions, one in the morning at 10 a.m. To 12 p.m. 12 noon, and the other one starts at 2 to 4. So we have invited speakers from all the IITs, NITs, and state universities, as well as industry universities, so that we can actually have interaction with all the people who are involved in the recent advancements taking place in the country. So by this FDP, I hope that you all will be getting benefited. The important announcement for this particular FDP is that The morning session link is different from the afternoon session. Please note it. So we will share that link in the WhatsApp group. So every day morning you have to log into the FDP using the link which you have shared now. And in the afternoon session, we will have a separate. I really would like to thank all the people behind me in getting this whole thing done. First thing, our chairman sir and the secretary sir, our director sir for guiding us, and then HOD of mechanical engineering, and my co-coordinator, Anand Babu, and all the organizing committee members who are behind all this. And I now request Madam to announce the next program.
Thank you, sir. So now I request Dr. PNE Naveen, Head of the Department of Mechanical Engineering, to speak a few words about this faculty development program. Sir.
Okay. Thank you, madam. Good morning. So first of all, I thank all the participants for registering towards our faculty development program. And I thank coordinators, Dr. G. Vijay Kumar Garu and Ananda Babu, for come forward for conducting these type of the FDPs. And the main aim of the FDP is to transfer the knowledge from the resource person to the lecturer level of the faculty. And in this, I want to, and I would like to thank all participants. So the main problem with these type of the programs is the nowadays, based upon the busy in the schedule, the faculty members are registering for any type of the program, but unable to attend the sessions. So in this, we want to bridge a gap for conducting and transferring the knowledge from resource person to the faculty members as a participants. So in this, I request all the members, please attend all the sessions so that definitely at the end of the program, you at least somewhat you can take away from this program. So all the participants attend, and if you have any queries, you can ask at any point of the time. The resource persons are also very quite simple and broad in the knowledge mindset. So you can ask at any time of the session and clarify your doubts. And this, I would like to thank all the registration by the faculty members as a participants and faculty members in the department. And finally, the management. The management is always looking to provide at what type of the infrastructure, what type of the benefit, what type of the support. So we can getting the things from the management, and depending upon their interest, we are conducting these type of the programs. So I thank all the members of the faculty members, management, and participants. So thank you, and one and all. At the end of the session, you get benefited. That is our aim of the program. Thank you.
Thank you, sir. Faculty Development Program is a celebration of knowledge. In this regard, it's my pleasure to introduce our today's resource person, Dr. N. Kishore Babu, who has graciously accepted our invitation to join us today. Dr. N. Kishore Babu, currently working as an associate professor in Metallurgical and Material Engineering Department at National Institute of Technology, Warangal, India, since April 2018. He did his master's degree in metallurgical engineering from Banaras Hindu University, Varanasi, India. He received a PhD in metallurgical and material engineering from Indian Institute of Technology, Madras, Chennai, India. He did postdoctoral research in the Safety of Joint Components Division of the Federal Institute of Material Research and Testing, Berlin, Germany from 2010 to 2014. He worked as an assistant research scientist in Joining Technology Group, Singapore Institute of Manufacturing Technology, Singapore. since 2014 to 2016. He worked as a scientist in Swiss Federal Laboratories for Material Science and Technology, Switzerland. His research interests are metal joining, nanocomposites, additive manufacturing. Dr. Kishore Babu has published 50 plus peer-reviewed publications in journals and conferences, a number of conferences and journal papers in 2009. Dr. Kishore Babu received the at Federal Institute for Material Research and Testing, Berlin, Germany. Each year, the prestigious Adolf Martin Fellowship will be offered to 10 selected fellows from all over the world for 1 year in the field of material science. He has completed 13 sponsored projects and guided 4 PhD students in the field of nanocomposites, welding, and additive manufacturing. So thank you for accepting our request, sir. Sir, can I hand over the session to you, sir?
Thank you. Am I audible?
Yes, sir, you are audible, sir.
Yes, sir. Good morning. You are audible.
Good morning, sir.
Good morning, sir.
Thank you. Thank you for your introduction. Distinguished guests, esteemed faculty members, dear participants, good morning to all. It gives me immense pleasure and honor to attend this program as an inaugural chief guest for this remarkable one-day faculty development program on recent advances in mechanical engineering. And I extend my heartfelt gratitude to NSRIT organizers for inviting me to be a part of this prestigious program. I am also thankful to Dr. G. Vijay Kumar Garu and Dr. V. Anand Babu Garu for inviting me for this program, and also for giving me the opportunity to give a talk on physical metallurgy and welding of titanium alloys that I am going to talk later. First and foremost, I would like to congratulate all the participants who have chosen to invest their time and effort in enhancing their knowledge and skills in the field of mechanical engineering. Your presence here today is a testament to your commitment to professional growth and your dedication to staying updated with the latest advancements in a mechanical engineering field. Actually, FDP programs play a vital role in the progress and evolution of any discipline. So by engaging this kind of FDP programs, we ensure that our teaching methodologies remains relevant and our students receive the best possible education. So mechanical engineering discipline is that has constantly evolved and contributed to numerous technological advancements across the various industries. In recent years, we have witnessed remarkable breakthroughs in this field. For example, recent new materials and also additive manufacturing process, robotic, automation, sustainable energy systems. So to name just a few. I have seen in the brochure also they are covering a lot of topics in this FDP, product design, dynamics, control of structures, FEM analysis, robotics. So one of the most exciting areas of research in mechanical engineering is the field of additive manufacturing. So additive manufacturing is also known as 3D printing. It is a process of creating objects by adding material layer by layer. So this process has potential to revolutionize the way we design and manufacture products. So another area of research that is gaining momentum is in the field of robotics. So robots are becoming increasingly sophisticated and they are being used in a wide variety of applications, from manufacturing to healthcare. Finally, I would like to mention in the field of energy, mechanical engineers are playing a key role in developing new technologies to generate and conserve energy. Events like this kind of FDP programs provides a platform for collaboration, networking, and exchange of ideas among faculty members and professionals in the field of mechanical engineering. So it gives me an opportunity for us to learn from one another, share our experiences, and foster meaningful connections that can lead to future collaborations and research endeavors. So I am confident that this FDP program will be valuable experience for all the participants. So I encourage them to take advantage for all that it has to offer. So I encourage the organizers to take note of suggestion from my side. and consider the feasibility of conducting future FDP programs in offline mode. So when circumstances permit. So the hybrid or blended format also another option. So we can combine both online and offline modes, and could also be explored and ensure wider participation and maximize the learning experience. So thank you again for giving this opportunity to be here today. And I wish you all the productive and enjoyable week. Thank you.
Sure, sir. We will note down your points, sir. Thank you for very much, sir. So, sir, our director, sir, is online, sir. So can I, sir, I request Dr. Raza Murugadas, Director, Nadimpalli Satyanarayana Institute of Technology, Sontiam, to speak a few words about this faculty development program.
Okay. Thank you, Ms. Usha. First of all, let me congratulate and compliment the entire team of Mechanical Engineering of NSRIT for hosting this 5-day FDP on the recent advances in mechanical engineering. At the same time, I would like to thank all the resource persons as well as Dr. Kishore Babu, who is inaugurating this 5-day FDP from NIT Warangal. Thank you, Professor. Certainly, this COVID has given a lot of opportunities to explore the various possibilities through online. However, as suggested, in future, we will have like a blended mode, having online and offline programs in collaboration with NIT Warangal and as well as with other institutions. So I don't want to take much time, Professor. Thank you very much for joining us. And once again, let me congratulate and compliment the entire team of Mechanical Engineering of NSRIT. And also, I request the participants to take this FDP in a fruitful way and to take the notes appropriately. Wishing you all the very best. Thank you.
Thank you, sir. So I request Mr. Ram Prasad Garu to give a vote of thanks. Ram Prasad, sir.
Just
Ram. Yes, sir.
sir, K. Ram Prasad, Assistant Professor, Department of Mechanical Engineering, NSRIT. Ladies and gentlemen, a very good morning to all. It gives me an immense pleasure to deliver the vote of thanks for this FDP to all the dignitaries assembled attended here. I would like to thank our chief guest who honored this function with his inspirational thoughts. I would like to thank our beloved management, director, and staff members and participants who have attended from all over the states, not only in Andhra Pradesh, Telangana, and outside AP and Telangana also. So many participants have attended. Nearly 105 participants have attended for this FDP. For this FDP on recent advances in ME. Once again, I thank one and all who are present here. Make utilize of this FDP, and I think this will be benefit for your research, and it will, and this will help for your PhD work also. Thank you to all. And next, the session will be started by the resource person, Kishore, Dr. Kishore. Thank you.
Good morning, participants. Actually, when I was speaking earlier, there was a YouTube live which was actually going on in the background. So I don't know whether you have heard my voice clearly or not. So please note that this is a link which I have shared. This will be useful for only morning sessions. Okay, in the afternoon session, we will share one more link. All the afternoon sessions will be running on that particular link. So please kindly note that. And I now request our resource person for the first session, Dr. Kishore Babu Garu, NIT Warangal, to start his session. Sir, Kishore sir.
Yeah, I'm sharing my screen.
Yeah, you can see.
So host to disabled participant.
Okay, sir. Okay, sir. Sir. Sir, I have given host to you.
Yeah, I'm checking. Can you screen my screen?
Yes, sir. Your screen is visible.
Okay, okay. Shall I start?
Yes, sir. You can start.
Okay. So once again, I welcome you for this FDP program on advances in mechanical engineering. So today I'm going to talk about physical metallurgy and welding of titanium alloys. So the outline of my presentation, which includes introduction of titanium alloys, influence of alloying elements, classification of different type of titanium alloys, and what are the phase transformations involved in this titanium alloys, and what are the different application of titanium alloys, and problems related to welding. There are three different types of titanium alloys: alpha alloys, alpha beta, and beta titanium alloys. And what are the problems that occur during welding? That also we are going to discuss, and defects in titanium welding. Titanium alloys possess high strength to weight ratio, excellent combination of strength and toughness, and good corrosion resistance, and low coefficient of thermal expansion and low thermal conductivity. So because of low coefficient of thermal expansion and low thermal conductivity, so these alloys make them actually welding point of view, it is very easy. Because high coefficient of thermal expansion means like aluminum alloys, it generates a lot of residual stresses. So, and also promotes solidification, cracking. This kind of problems will be there. But in titanium alloys, because of low coefficient of thermal expansion and low thermal conductivity, this problem during welding was less. But because of all these properties, make them attractive for different applications like aerospace industry, pressure vessels, surgical implants, and aircraft applications, chemical industry, marine and petrochemical industries, and also manufacture of sports equipment also. Titanium alloys can be used moderately at elevated temperatures, for example, in the range of 370 to 595 degrees. And especially these alpha alloys you can use for creep application, mainly for high temperature applications. So if you take example of titanium alloys that compromise approximately 42% of the airframe weight of the new F-22 fighter aircraft. So in commercial passenger aircraft engines, titanium alloys are used for the fan, a low pressure compressor, and approximately 2/3 of the high pressure compressor also. So you can see different types of applications, different types of properties of titanium alloys: high corrosion resistance, low specific gravity, and it is also biocompatible, non-magnetic property, and high specific strength. So pure titanium generally shows a silver color metal, and melting point is slightly higher than steel, 1670 degrees, boiling point 3260 to 260 degrees, and the average coefficient of thermal expansion is 8.41, and the density 4.51 gram per centimeter cube. Titanium always forms, it has strong affinity for oxygen. That's why it always forms oxide layer on the top surface of the titanium. So that is this oxide film makes titanium passive to further reactivity. So because of this reason, it possesses excellent corrosion resistance to aqueous salt or oxidizing acid solutions, and to above average resistance to corrosion caused by many mineral acids. So if you take this cost of titanium for comparison, if steel ore cost is only $0.2 per LB, but titanium it is $0.22 per LB. If you take sheet, if the steel is only $0.3 to $0.6 per LB, but in titanium its cost is very high, $15 to $50 per LB. So because high cost of titanium compared to others like steel and aluminum, it is because of high extraction cost and also high processing cost. So this processing temperatures they are used for titanium is very low processing temperature, and also the conditions the surface regions get contaminated very easily at this processing temperature. So these surface cracks and should be removed after processing. So it requires a high cost. That's why titanium sheet cost is it varies from $15 to $50 per LB. And also metal consumption of different materials you can see here. Titanium, it's very less because of high cost, 50 into 10 power 3 metric tons per year, compared to steel and steel 700,000, aluminum 25,000. So these are the density of the metals you can see here. Titanium density is approximately 4.5 gram per centimeter cube. Compared to iron, nickel and copper, it is slightly lesser. And another light metal, still you can also see the very light metals, lithium only 0.87 and magnesium 1.6 and aluminum 2.7 gram per centimeter cube. This titanium alloys has interesting properties of low density, high melting point, low coefficient of thermal expansion, and outstanding corrosion resistance. This we already discussed in the previous slides. So titanium alloys possess much better values of specific strength. You see here, titanium alloys possess much better values of specific strength. That means high strength to weight ratio compared to aluminum alloys or steels and super alloys. So these specific values for different alloys you can see here. So the combination of high strength, good toughness, good corrosion resistance make it saving applications in aerospace structures, chemical and petrochemical applications, and also alloys also being used in marine environments, biomaterial applications. So if you see this macro graph of forged grade 2 titanium, so grade 2 titanium in the top surface, if you see, there is oxide layer which is present on the surface. So this oxide layer makes the titanium passive to further reactivity. So because of this, it possesses excellent corrosion resistance. Titanium at room temperature, it shows alpha, it is a HCP structure, and at 882 degrees, alpha changes to beta phase. Beta is a BCC structure. It is just like phase transformation. In steel also we have seen, if you take any carbon steel, there will be austenite, and below ferrite, perlite will be there. So some phase transformation will take place. Similarly for titanium, at room temperature it is alpha structure, but if you hit the temperature 882 degrees, it changes from alpha to beta. Beta is a BCC structure and alpha is a HCP structure. So the temperature at which phase transformation takes place, that is called transformation temperature. So if the alloy is slowly cooled from the beta phase region, then you will get diffusional alpha. If the alloy is quenched from the beta phase, then you will get a martensite phase, that is alpha prime, which is also HCP. So there are different alloying elements that stabilizes the alpha and beta phases. Mainly alpha stabilizers are, principal alloying element is aluminum, and remaining stabilizers are carbon, oxygen and nitrogen. Beta stabilizers mainly two types, isomorphous and ectoctide. Isomorphous means completely soluble in the liquid in the both phases. So isomorphous means they stabilize, the stabilizers are niobium, molybdenum, vanadium and tantalum. Ectoctide stabilizers are chromium, nickel, cobalt, iron, manganese. So copper, silicon also. So some these are neutral elements are tin and zirconium. So they neither stabilize the alpha or beta phase, but these elements are mainly used for solid solution strengthening. So here important point is the temperature at which allotropic transformation takes place. That is called beta transverse temperature. So for CP titanium, the beta transverse temperature is approximately 882 degrees centigrade. So this is the titanium crystal structure. So as I already mentioned, alpha phase is HCP and beta phase is BCC. Here you can see different planes are present in alpha phase. So pyramidal, prismatic, and basal plane also you can see here. So mainly SCP-allies, if you take deformation is limited because limited number of slip systems are available. That's why it relies on twinning. And BCC phase is it contains many slip systems are available, so that deformation is very easy if the BCC phase is retains at room temperature. So depending upon the alloying elements, you can classify the titanium alloys into CP titanium, alpha alloys, near alpha alloys, alpha beta, and beta alloys. So this is a neutral alloying elements like tin and zirconium. So they neither raise or nor lower the beta transist temperatures, but mainly used for solid solution strengthening. So if you add alpha stabilizers like aluminum or carbon, oxygen, or nitrogen, then it raises the beta transist temperature. Whereas when you add beta stabilizers, so it lowers the beta transist temperature. But when you add alpha stabilizers, it raises the beta transist temperatures. Beta isomorphous again divided into two types, isomorphous and hetactide. So isomorphous means the solubility of the element in titanium in the beta is unlimited. So when you are adding more beta stabilizers, so it starts decreasing the beta transist temperature. So beta hetactide means one solid become converted into two solids. So the alpha plus intermetallic compound you can see here. So SN and zirconium I already mentioned. These are neutral elements. They mainly used for improving the solid solution strengthening. So generally this solid solution strengthening, mainly zirconium that forms continuous solid solution with the titanium and increases the strength at low and intermediate temperatures. So these are the classification of different types of titanium alloys. So CP titanium means commercially pure titanium. So different grades you can see, depends upon the oxygen content, the grade will vary. Some CP titanium alloys containing PD, palladium additions. So the main purpose of adding palladium is to increase the corrosion resistance. So second one is alpha alloys. So this principal alloying element is aluminum, and it does not influence the transformation temperature, but it causes a but these alloys containing some amount of tin or zirconium, so it does not influence the transformation temperature, but it is used for solid solution strengthening. Main principal alloying element is aluminum, so it also contributes to high strength to weight ratio also. These alloys possess good high temperature applications, like good high temperature stability and suitable for creep application. And these alloys are not amenable to any heat treatment. Near alpha alloys also contains some small amount of beta stabilizers. So you can add up to 2-8% beta stabilizers, so that it can still improve the creep resistance. So these alloys generally contain some amount of silicon to improve the creep resistance. Alpha beta alloys, generally these alloys contain significant amount of beta stabilizers. Like when you add these alloys contain up to 6% beta stabilizers. The most famous alpha beta titanium alloy is the titanium 6 aluminum 4 vanadium alloy. So these may also contain some amount of neutral elements like tin and zirconium for solid solution strengthening. These alloys you can do heat treatment. You can do some finishing operations also. You can improve the properties by doing some heat treatment operations. So these alloys you can use up to 450 degrees centigrade. For example, titanium 6 aluminum 4 vanadium alloy, you can use up to 450 degrees. So beta alloys again divided into two types, metastable beta and beta, that I am going to explain a little later. If the beta stabilizer content is greater than 10%, then beta will be even retained even at room temperature. So that is called beta. Because of good ductility of the beta phase, beta alloys you can do forming operations, excellent formability, and also these alloys possess excellent forgeability, code rolling capabilities. So these are the CP titanium microstructure, you can see this is a commercially pure titanium, grade 2 titanium plate. You can see very fine equiaxial grains in this. So these alloys also containing sometimes intentionally they will add 0.2% palladium for improving the corrosion resistance. So generally the CP titanium is quite ductile. These alloys mainly used in chemical plants. These alloys possess yield strength in the range of 240 to 550 and UTS in the range of 260 to 621. Pure titanium is quite ductile and you will get elongation percentage 15 to 25%. So adding limited amounts of oxygen and carbon nitrogen in solid solution will significantly strengthen the titanium. So when you are adding more amount of oxygen, that means strength will increase, but ductility will drastically decrease. That's why you need to control the oxygen and nitrogen content. Otherwise, when the oxygen and nitrogen content increases, it promotes the embrittlement actually. Similarly, hydrogen also promotes embrittlement in titanium when present above specific limits. That's why even ppm levels of hydrogen also promotes the hydrogen embrittlement. So in this, if you see strengthening by cold working also possible but not popular. But if you take aluminum alloys, it is FCC crystal structure. When you do cold working, it improves the mechanical properties. Because of SCP structure, only limited number of slip systems are available. That's why cold working is possible but not popular. So when you are adding, if you see this phase diagram, when you are adding this alpha stabilizers, it raises the beta transition temperature. For example, if you are adding oxygen, nitrogen and carbon, so these are the alpha stabilizers. It raises the beta transition temperature mainly. And when you are adding these elements, interstitial elements like oxygen and nitrogen, so they have extensive solubility in the alpha phase, but with oxygen having the greater stability. Hydrogen is more soluble in the beta phase than alpha phase. So this is the effect of interstitial content on strength and ductility of pure titanium. So if you see, when you are adding impurity content like oxygen, nitrogen or carbon, its strength is keep on increasing. So here the strength is approximately 450, 410 or 420 MPa. But when if you are increasing the oxygen content, so its strength goes to up to 800. So when you are adding this interstitial content, strength drastically will increase, will improve, but ductility, if you see, drastically decreases when you are adding when you are increasing the impurity content. So nitrogen is a more effective strengthener, followed by oxygen next, then followed by carbon. So the effectiveness of carbon is hindered by limit of solubility, so that titanium carbide compounds has a little strengthening effect compared to nitrogen and oxygen. Hydrogen is also soluble in the beta as well as alpha phases, but beta phase has a much higher solubility. If you see this phase diagram, it is an atomic percentage you can see on the x-axis. So beta phase has a maximum solubility of approximately 48 atomic percentage. So that is approximately 2 to 8% is possible in the beta phase. The high solubility, rapid diffusion of hydrogen in the beta phase results from the BCC structure, and also hydrogen enters into tetrahedral holes which are larger in BCC than HCP. So that's why the solubility is more in the beta phase. So the presence of the hydrogen in both alpha and beta phases results in lattice expansion. It also promotes the hydrogen embrittlement. If the alloy is slowly cooled from the alpha region to room temperature, generally these hydrates starts precipitating out, so that it promotes the hydrogen embrittlement. So hydrogen is only slightly soluble in the alpha phase. It is soluble only up to 8 atomic weight percent, but that is approximately equivalent to 0.158%.
If the Li is slowly cooled from the alpha phase fields, the hydrate starts precipitating out. Even if you cool slowly, it causes a notch sensitivity because hydrate starts precipitating out throughout the alpha grains and also at the grain boundaries. When you quench it from the alpha phase field, hydrogen to precipitate throughout the alpha grains in a very fine particles, but it will have little effect on sensitivity. But when you start aging, again this agglomeration of hydrates will takes place, and again it will increase the notch sensitivity. So beta alloys, I already mentioned, it can dissolve more hydrogen, approximately 49 atomic percentage, which is equivalent to 2.08 weight percentage. Then alpha air. So alpha beta alloys will dissolve a considerable amount of hydrogen without the formation of hydrates. So these are the microstructure of the CP titanium. The first one, it shows equiaxed grains. So if it is annealed at 700 degrees, it is showing equiaxed grains. If you quench from the beta phase field, just like if you take steel and to the austenitic region, and if you quench, you will get martensite. Similarly, if you take the if you hit the alloy to beta region, and if you quench, you will get martensitic kind of microstructure. You see here needle kind of microstructure. And the third one is if you air cooled from the beta phase field, you will get this kind of Wittmann-Staten plates of alpha. And fourth one is near alpha microstructure. It is a kind of microstructure. It is showing mainly basket wave type of microstructure in which alpha platelets were densely packed in a beta matrix. The white one is alpha and dark lines are the beta phase field. So these are the composition of different CP titanium alloys. So grade 1 means if you see on the right hand side oxygen content, grade 1 contains only 0.18% oxygen weight percentage. Grade 2 0.25. So with increase in grade number, oxygen content also increases. So strength also will increase, but ductility will be drastically decreased. Alpha alloys, I already mentioned, aluminum is the principal alloying element. So these alloys also containing zirconium and tin. These are neutral elements mainly added for improving the solid solution strengthening. These alloys possess good high temperature properties and weldability, and these alloys are not amenable to any heat treatment. These alloys you can use for cryogenic applications also. You can see these are the different grades of CP titanium alloys or alpha titanium alloys. These alloys containing some amount of oxygen also you can see, and beta transverse temperature for these alloys also given here, and yield strength and tensile strength values also you can see. So this is the phase diagram between titanium and aluminum. And when you are adding aluminum, so up to 6%, up to 8%, you can add in commercial titanium alloys. So if it is crossing greater than 8%, so mainly intermetallics are forming. You see here. So in this region, Ti3Al is forming. At this region, TiAl is forming. And here also greater than 50% aluminum, it is also forming TiAl2 and TiAl3. So when you are increasing the aluminum content, so embrittlement occurs. Mainly intermetallic compounds are forming, so that is not beneficial. It promotes embrittlement mainly. So that's why there is a limit to add aluminum content in titanium. So up to 6 to 8% is okay in commercial alloys. If it is greater than that, many intermetallic compounds will form. So if you see here, if the aluminum content is in the range of 14 to 26, it forms Ta3Al. 34 to 56, it forms TiAl. These are all intermetallic compounds. So generally, the stability of the alpha phase can be measure of that alpha phase stability can be defined by using this equation called aluminum equivalent. Aluminum plus tin by 3, zirconium by 6, and 10 times the oxygen plus. When you are adding small amount of oxygen, carbon or nitrogen, because it is multiplied with 10, aluminum equivalent will increase. So if it is crosses greater than 8% means, then it's a problem, embrittlement occurs. That's why you need to keep the aluminum equivalent less than 9%. so that you can use for commercial applications. Similarly, you see here aluminum content. If you are adding greater than 8%, it starts ductility starts decreasing, but strength increasing. You see up to 9%. When you are adding aluminum content, strength increases, but ductility starts decreasing because of this embrittlement problem. So these are the example of different CP titanium welds used in heat exchanger applications. These are commercially P titanium alloys used in different applications in power plants and also other applications. You can see water plants, pulp and paper industry, chemical industry, mineral dressing, biomedical devices, spacecraft, and you can see the specific equipment from this power generation industry, water plants, and also environment they are using in this industries also you can see here. So near alpha alloys, we know that alpha alloys principal alloying element is aluminum. In near alpha alloys, it contains some amount of beta stabilizers. You can add up to 2 weight% by weight, and these alloys also possess higher creep resistance, and majority of these alloys containing some amount of carbon, some amount of silicon, mainly for improving the creep resistance. So these alloys you can use up to 500 to 550 degrees centigrade. So these are the example of these alpha titanium alloys: titanium 6242, dimetal 1100, dimetal 685. These are the examples. You can also see the mechanical properties here, and fracture toughness. These alloys also possess good fracture toughness, also greater than 50 MPa root temp. You can see here. So next classification is alpha beta alloys. So these alloys containing some significant amount of beta stabilizers you can add in this up to 6 weight%. So these alloys also containing tin and zirconium as a solid solution strengtheners. So these alloys you can do heat treatment for these alloys, but near alpha alloys you cannot do any heat treatment. But creep strength is lower than near alpha alloys. So these alloys either you can use in annealed condition or solution treated under aged condition. So these alloys exhibit high strength to weight ratios in heat treated condition, and also these alloys possess good fracture toughness. So the fracture toughness in the range of 65 to 110 MPa. The most famous alpha beta titanium is the Ti64, titanium 6 aluminum and 4 vanadium alloy. Aluminum is alpha stabilizer and vanadium is the beta stabilizer. These alloys possess yield strength in the range of 800 to 1100, and ultimate tensile strength in the range of 900 to 1200 MPa, and a good percentage of elongation also. Good ductility also having 13 to 16%. Phase transformations of these alpha beta alloys you see here. This is a pseudo binary phase diagram. Titanium left hand side you can see the temperature, and you vary the beta content here. Vanadium content, vanadium is a beta stabilizer. You are varying beta content here, and titanium 6 aluminum vanadium composition lies in this. You can see here. So this is the titanium 6 aluminum and 4 vanadium. And suppose if alloy is heated to above beta trances. So beta trances means, I already mentioned, it is the temperature at which alpha plus beta changes to beta phase here. So approximately the beta trances temperature for this alloy is 980 degrees centigrade. So suppose if the alloy is heated to above beta trances temperature, for example 1050 degrees, and if you are cooling slowly from this temperature, like furnace cooling, then you will get a lamellar kind of microstructure. So it is alternative layers of alpha plus alpha and beta. White areas is alpha and dark lines are beta phase. Just like similar to perlite. If you heat the steel to austenitic region, then followed by slow cooling means you will get ferrite and perlite, right? Similarly, here also you will get a laminar kind of microstructure, that is alpha and beta. White areas are alpha and dark lines are beta. So, and rapid quenching leads to, if you are quenching from this region, so then you will get a martensitic microstructure. So if you quench from this region, it is a kind of martensitic microstructure. So this is very hard compared to furnace cooled one. If you do tensile test, it possesses good high strength and low ductility. So at annealing temperature of, if you see here, at annealing temperature of 800 degrees, 800 degrees. So the vanadium content of beta phase is approximately, so when you dot tie line here, the vanadium content of beta phase is approximately 14%. So that is sufficient to place the MS temperature below room temperature, so that so when you heat the alloy at 800 degrees, and if you quench it, you will not get the martensite. So you will get martensite only if you heat above 800 degrees centigrade, and if you quench it, then definitely you will get the martensite. But at 800 degrees centigrade, problem is that the vanadium content of beta phase is approximately 14%. That is sufficient to place the MS temperature, martensite starting temperature below room temperature. That's why even if you quench from 800 degrees centigrade, you will not get the martensite. Even if you air cooled from this temperature also, from 1050 degrees, from 850 or 850 degrees, then you will get this kind of coarse lamellar microstructure only you will get. If it is a furnace cooling, if it is lamellar, and still from 800 degrees, you will get the coarse lamellar kind of microstructure only you will get. So this is a similar kind of diagram, pseudo binary phase diagram, titanium 6 aluminum you can see on the left hand side, and varying vanadium content. And the main problem here is at 840 degrees, this is 840 degrees. If you quench from this temperature, you will not get martensite, because the vanadium content of beta phase is approximately 14%. That is sufficient to place the MS temperature below room temperature. Even if you quench from the beta phase field, you will not get 100% martensite, because the martensite finishing temperature is below room temperature, so that some retained beta will be there. Similar to austenite also, even if you quench, you will not get 100% martensite even in steels also, because some retained austenite will be there. Similarly, retained beta will be there in titanium alloys. Same thing explained here. This is the continuous CC diagram for alpha beta titanium alloys. So during continuous cooling, here you can see here continuous cooling of alpha beta titanium alloys, and this line is beta to alpha transverse temperature, and this is the finish of beta to alpha temperature, and in between you can see the alpha plus beta and different cooling rates. So during continuous cooling, what will happen? Principally, the decomposition of beta occurs, so that transformations like diffusional control transformation, like nucleation and growth of alpha formation will take place. If you quench fast, like this curve, these are the fast cooling, then you will also get diffusionless or shear transformation to martensite. Or sometimes if it is in between, then you will get a mixed mode of transformation. That is, initial transformation is a diffusional transformation, then it is interrupted by martensitic transformation. So here you can see the different cooling curves superimposed on this diagram, A, B, C1 and C2. You can see here cooling rates right of the C2. Right of the C2 means very slow cooling rates. So here you will get a coarse lamellar kind of microstructure. So cooling rates left of the C1, this is a critical cooling rate. If the cooling rates are very fast, means then it is directly touching this martensitic starting line. This alpha prime is the martensite. So if it touches this line, then you will get the martensite. So if the alloy is in between, you see here C1 and C2, there is one line. If the cooling rate is in between, means initial transfer, if it touches this line, initial transformation is diffusional transformation. You will get lamellar product here. Then it is interrupted by martensitic transformation. So here you will get a mixed mode of transformation. So this is transmission electron microscopy of EB wells of Ti64 wells. This is one of my research paper published in Science and Technology of Welding and Joining. Here you can see how the martensitic microstructure will appear. These are the TEM micrographs, transmission electron microscopy figures. Here you can see the alpha prime martensite in a zigzag fashion. And also you can see the lines present here. These are the dislocations. And we also obtained diffusional product also. That means we got a mixed mode of transformation. So initial transformation is alpha beta transformation. That means a diffusional product you will get, and then which is interrupted by martensitic transformation. When you do aging for this martensitic microstructure or this retained beta, when you do aging for Ti64 alloy, the fine dispersion of beta in alpha is formed. Alpha starts precipitating out from the beta phase, and also you can see the beta particles also start precipitating out from the alpha prime. Beta alloys, it contains sufficient amount of beta stabilizing elements. So greater than 10%, when you add beta stabilizers, it retains beta even at room temperature. That means there is no alpha phase. So when you are keep on adding beta stabilizers, that means greater than 10% it can retain the beta phase. Because of good ductility of the beta phase, beta alloys possess excellent formability, and also these alloys possess excellent portability and cold rolling capabilities. You can easily weld these alloys in the annealed condition. So most famous alloys are titanium 1533. These alloys contain 15% vanadium and 3% chromium and 3 aluminum and 3 SN. And also in the annealed condition, you see here yield strength in the range of 800 to 1000, tensile strength 800 to 1100. When you do aging, still you can increase the strength, but ductility will be decreasing. So beta alloys again divided into two types: metastable beta and stable beta alloys. So if you see here, this dotted line is the MS martensitic starting temperature, and this line is the beta starting beta transverse line. This line is called. So if it is in between means, then it is called metastable beta alloys. So if the beta stabilizing element crosses this beta S point, then it is called stable beta alloys. So the critical minimum level, that is called beta C. And here beta C means where this MS line intersects the room temperature axis. So in between this region is called metastable beta. So metastable beta also contains some amount of alpha stabilizers. But stable beta means when you are adding more amount of beta stabilizers greater than 10%, this beta phase will be retained even at room temperature. So these are the beta stabilizers. You can see vanadium, niobium, these are the different beta stabilizers. The stability of the beta phase can be defined by using this formula called molybdenum equivalent. Molybdenum plus 2.5 times iron, 1.7 cobalt. Here you can see. So these elements are iron, chromium, iron, cobalt, manganese, nickel, and chromium. Solutes more effective than molybdenum. So because it is multiplied with 2.5 times, 1.7 times. So these elements are less effective than molybdenum. 0.67 weight%, 0.67 multiplied with vanadium. So these are the less stable. Suppose this molybdenum equivalent is 0 to 5%, these are beta rich alloys. And if it is 5 to 10%, that is near beta, metastable beta means if it is in between 10 and 30%, these alloys are called metastable beta alloys. So if the molybdenum equivalent is greater than 30 means that is completely stable beta. So these are the example of different metastable beta and beta alloys. So 10.2 means this is metastable beta alloy, and stable beta means if it is 30 and above, it is called stable beta alloys, molybdenum equivalent. And here you can also see the different beta transist temperature for these alloys. So influence of alloyingation on concentration of on alloy concentration necessary to retain 100% beta. So because some alloying elements in the previously I showed, like iron, cobalt, these are more effective than below elements. So that's why when you are adding iron, only 3.8% that can retain the 100% beta even at room temperature. So that's why 3.8% iron added to titanium is required to retain the beta phase even at room temperature. But when you are adding for only tantalum means if you want to add to retain the beta phase at room temperature, then you need to add 45.8%. So that is the difference between different alloying elements on beta phase stability. So metastable beta alloys, these alloys these alloys possess BCC structure. Because of number of slip systems are available, you can do readily cold working in the beta phase field. And after quenching, you will get equiaxial beta phase. These alloys you can do heat treatment. The first step is heating the above beta transverse temperature, then followed by quenching, and then you do the aging heat treatment at generally 500 to 600 degrees. Then you will get the alpha starts precipitating out, and you can increase the strength, but ductility will be drastically decreased. These alloys possess excellent fabricability, good tensile strength. These alloys, when you start adding beta stabilizers, its creep strength will be decreased. Good weldability, and this is the example of metastable beta alloy. These alloys are generally used in the solution treatment and aged condition. Another one is the decomposition of the this metastable beta that can occur mainly during aging temperatures. So mainly omega phase is placing the vital metastable phase that is formed mainly in metastable beta titanium alloys. So you cannot resolve this phase in optical microscope. For that we need TEM. So this omega phase that can be formed athermally or isothermally. Athermal means during quenching or during cooling itself, these alloys will form. So if you see here, if the alloy content is less means this athermal omega will form during quenching itself. Then it is called athermal omega. This athermal omega is believed to form without change in chemical composition. This is similar to martensite, and this will have little effect on quenched and mechanical properties because of low volume fraction. Suppose if you are heating this metastable beta alloy in this temperature range, for example 300 to 350 degrees centigrade, and you are holding for sufficient time means, then this isothermal omega starts precipitating out in this region. That means this omega, suppose if you are keeping for more than 24 hours at this temperature 250 to 500 degrees, then its omega starts precipitating out. Then it is called isothermal omega. This isothermal omega has composition intermediate between alpha and beta, and when you are keep on increasing the aging time, this omega will act as a precursor for the formation of alpha phase. If the isothermal omega percentage greater than 50% means, then embrittlement problems occur. But still, if you are adding more solute content, then beta prime starts precipitating. Generally beta prime is a solute lean phase, and this will act as a precursor phase, and as temperature increases, as the aging time increases means alpha starts precipitating out from the beta prime phase. So generally in metastable beta alloys, two-step aging is preferable. Generally first step aging, if you do at 300 degrees and second step aging at 500, in the first step aging,
most of the faculty and the same subject also.
the LI content is low, omega phase will form. LI content is high, beta prime will form. That's what we wrote here. Precursor phases like in the first step aging, this will form, and omega and beta prime phase. Upon which, if you aging still continuous means this will act as a alpha starts precipitating out. This fine alpha platelets will form. That is responsible for increasing the strength. So if the overaging means there's alpha platelet starts coarsening will increase, then your strength will decrease. But during aging in general, if the fine alpha platelets forming means generally strength will increase and ductility will be decreased. So these are the so far we discussed about alpha alloys, alpha beta and beta alloys. So alpha alloys generally used for high temperature application, creep application. So when you are adding beta, increasing beta content, its heat treatment response will increase. In alpha alloys are not amenable to any heat treatment, but heat treatment response will increase. But creep strength will decrease in this region and beta region. But here you can see increasing alpha content. When you are adding more alpha stabilizers, then creep strength will increase. From right hand side to left hand side, these alloys mainly for creep strength, these alloys mainly for improving the heat treatment capability will increase, and also mainly suitable for fabricability. I mean, that means suitable for cold rolling applications. So these are the different example of alpha, alpha, beta, and you can see the mechanical properties. So the alpha beta alloys generally it varies from 800 to 1000 MPa yield strength, and ultimate tensile strength you can go up to 1100 MPa. But beta alloys still higher you will get because alpha start precipitating out during aging. So these are the example of titanium 6 aluminum 4 vanadium alloy used in jet engine applications. So these are jet engine fan disc you can see here. These are modern aero engines. Generally, the weight share of titanium is approximately 25%. You can see titanium fan, vane frame, titanium fan disc. So all these parts are made of this titanium alloys. Tucummo dome with a retractable titanium roof also you can see here. Titanium alloys also used in sports applications. The metastable 1533 beta alloy, it is also used for handlebars and seat posts of mountain bikes, and some sporting goods like golf clubs, tennis rackets, bicycle frames. So these are also made of titanium alloys. And metastable beta alloys, especially these beta titanium alloys, you can use in because these alloys possess low modulus and high strength. That's why these alloys are used mainly for automotive, suspension coil, rotor, connector applications. So nowadays, many parts used for automobiles were made of steel that can be replaced with the beta titanium alloys. So the main advantage, weight saving applications you will get by replacing with these alloys. And titanium alloys also used in human body applications and dental applications. Here you can see hip or knee prosthesis, good corrosion stability in the human body, and these alloys possess good fatigue resistance, high strength to weight ratio, low elastic modulus. So beta titanium alloy, especially low elastic modulus compared to other alloys. So the low elastic modulus particularly relevant because of an important requirement for bone replacement. So far we discussed about alpha, beta and beta titanium alloys. now I'm going to talk a little about titanium welding. When you are doing titanium welding, titanium readily pick up gases like nitrogen, oxygen, hydrogen, and these are interstitial elements that can easily enter into the titanium lattice if the temperature exceeds 430 degrees. So it occupies interstitial sites so that basically it reduces the number of systems. So the strength increases, but ductility decreases. It basically number of dislocation systems also will decrease. So because of that, deformation is not that much easy. And here also you can see if the interstitial elements are present, if it exceeds certain limits, then stresses generated during welding may cause cracking also. Here you can see the cracking. And generally the levels of oxygen on the order of 3000 ppm in the weld metal may be acceptable. If it exceeds, generally cracking occurs in the weld metal zone or heat affected zone. That's why when you are doing arc welding with titanium alloys, we know that in TIG welding or MIG welding, we will use argon or helium as a shielding gases. But in addition to torch gas, we need to provide backing and trailing gases also for welding titanium alloys. Otherwise, these elements can easily enter into the weld metal and it degrades the mechanical properties, and sometimes it promotes the cracking also. So generally, above 450 titanium tend to oxidize more rapidly, and if you don't remove the oxide layer, then it is a problem. That's why you need to use a protective shielding such as inert gas atmosphere, like argon shielding. Trailing and backing gases also you need to use. And another advantage is the relatively low coefficient of thermal expansion and conductivity of titanium, so reduces the possibility of distortion caused by welding. So generally, aluminum alloys possess high coefficient of thermal expansion. Then it is a problem. Lot of distortion problems will occur. But those problems are not there in titanium alloys because of low coefficient of thermal expansion. And thermal conductivity is 1/2 of the stainless steels and 1/10 of the aluminum alloys. So in aluminum alloys, because of high thermal conductivity, heat cannot concentrate at one point. You need to use high currents and high heat input also. But because of low conductivity of titanium alloys, you can use low currents also. And linear coefficient of thermal expansion of titanium is generally lower than of aluminum alloys and steels also. And electrical resistivity of titanium also lower than precision hardened stainless steels and 10 times greater than aluminum alloys. If hydrogen and oxygen absorbed, generally it can easily enter into the weld pool if the moisture is present on the sample. That's why before welding you need to remove the oxide layer by using stainless steel brush to remove the oxide layer, and also you clean with acetone. If necessary, sometimes you can do pickling operation also, so that you can remove the hydrogen and oxygen content, or if any moisture present on the sample. If you don't remove the oxygen, these elements, interstitial elements, can easily enter and it degrades the mechanical properties. Titanium alloys are extremely reactive and sensitive to contamination, and you can use a different welding process like GTAW, gas tungsten arc welding, gas metal arc welding, plasma arc welding, electron beam welding, laser beam welding. You can also weld with friction welding also possible. And important point is high purity shielding gases you need to use, and also backing and trailing gases. If there is no backing and trailing gases, you can also try with the glove box welding. So you need to fill the glove box with the argon atmosphere, and you can do the welding. No serious hot cracking problems like aluminum alloys, but if the impurity content increases, then only it promotes cracking. Patching fillers also available. Limited availability of filler wires. You can if you use electron beam or laser welding process, if you use electron beam welding especially, it is the process is carried out in vacuum, so you will get very high quality welds compared to arc welding. So most alloys suffer from poor weld ductility. So all these problems you can avoid by choosing proper shielding gases and arranging proper backing and trailing gas arrangement. And you need to remove the surface films before welding and thoroughly degrease the weld joint before welding. So these are the microstructure of the different titanium alloys. These are the microstructure of the metastable beta titanium 1533 alloy. You can see the equiaxial grain present in the fusion zone, and epitaxial growth occurs that can occur from the prior beta grains present in the base metal or in the heat affected zone. You see epitaxially that are growing from the beta grains. The beta grains that are present at the edge of the fusion boundary will act as an ideal substrate for the growth of the grains. So this kind of growth is called epitaxial growth. And because of high thermal gradient that are present in the laser wells, so you can see coarse columnar grains that are extending from the fusion boundary towards the weld center. And I already mentioned about these interstitial elements like oxygen, hydrogen, and nitrogen. If they present in the weld metal, it degrades the mechanical properties. So poor ductility mainly associated with large prior beta grains and acyclic martensitic. If any martensitic microstructure that is present in the weld metal means strength will increase, but ductility will be drastically decreased. So in order to, if you want to improve the ductility, either if it is a GTA welding, then you can do pulsing or some, you can manipulate the arc, or you can also try with arc oscillation. You can use low heat input process like electron beam welding, or you can do post weld heat treatment mainly necessary to improve the weld metal ductility to an acceptable level. These are the microstructure of the base metal. After welding, this TM micrographs, you can see this white area is alpha and dark one is dark lines are beta. Alpha parallel platelets you can see separated by beta phase in between them. And after when you do any current pulsing technique in GTAW, the grains will be refined and you will get good strength and ductility. Well, generally, if you are using any welding process, it generates some kind of residual stresses. And also, if you use a low heat input process like electron beam welding, you will get martensitic microstructure, especially these alpha beta titanium alloys. The main purpose of doing post weld heat treatment is to relieve of residual stresses, or you can modify the metastable weld zone microstructure, and you can stabilize the microstructure for weld structure application, and you, at elevated temperature you can use. The ultimate aim of post weld heat treatment is to enhance the mechanical properties. So generally this post weld heat treatment for near beta and alpha beta titanium alloys, you can carry it out at 400 to 550 degrees centigrade, so that micro precipitation of beta that will starts coming out, that can precipitate from the alpha prime martensite, and also some alpha start also precipitating out from the beta phase also, if any beta that retains in the microstructure. So especially this beta alloys, no serious cracking problems. Main problem with the beta alloys is grain boundary alpha formation is even during welding also it will form. Even when you do post weld aging also, still it thickens and it decreases the ductility. Segregation problems and non-uniform strengthening precipitates that are forming throughout the weld, that is a problem. So you must either compromise on a strength or ductility. So generally in the as welded condition, you will get low strength, but when you start aging at 500 degrees centigrade, so alpha start precipitating out, then strength will increase, but ductility will be drastically decreased. So this is the metastable beta titanium alloy, titanium 10-3. Here you can see the continuous grain boundary alpha that is forming. When you do tensile test, actually the stress concentration will take place in this region. It generates triaxial stresses, and the metal strength can improve, but ductility will be drastically decreased. because of this grain boundary alpha. So this we already discussed. So if you want to control this, if you want to reduce the grain boundary alpha, you can choose another filler metal like in the alpha plus beta region filler or CP titanium filler, so that it can shift the metastable beta region to the left hand side, so that it can shift to the alpha plus region, beta region, so that you can improve the ductility. So generally for metastable beta alloys, two-step aging generally preferable. In the first stage of aging at 300 degrees centigrade, either omega or beta prime will form. It depends upon the alloy content. And when you do aging at 500 degrees centigrade, whatever the phases, whatever the precipitate that are forming at 300 degrees centigrade, like omega or beta prime, that will act as a precursor phases upon which alpha starts precipitating out. So generally, if any coarser alpha platelets are generally there, means ductility will improve. If fine alpha platelets means strength will improve, the ductility will be drastically decreased. So these are generally weldability issues for different titanium alloys. CP titanium and alpha alloys, these are generally weldable and good ductility also will get. Alpha beta alloys are weldable, but because of a large amount of alpha prime Martin side, ductility will be less. And metastable beta alloys are weldable, good as well ductility will get. But when you do aging, grain boundary alpha will form. That is a problem. Strength will increase, but ductility will be drastically decreasing. So these are the main defects in titanium alloys are mainly weld metal porosity you will get if you don't choose proper shielding, then these gases may enter into the between the dendrites, and it's difficult to escape. That's why this porosity will form. Embrittlement mainly occurs because of hydrogen or nitrogen or oxygen contamination. Mainly contamination is the main problem. So another problem, another defect is this is the based on weld color you can judge the weld quality. So if it is silver color means you applied correct shielding, and this is a good one. Light straw to dark straw, this is slightly, the surface is slightly contaminated. If it is purple or blue color means heavily oxidized. This is not suitable. This weld is not suitable for real-time applications. So gold color is slightly acceptable, but purple and purple is a moderate surface contamination, but blue color means it is not acceptable. Dark blue to light blue, heavy contamination. Yellow to gray to white also, these are also heavily contaminated, and these are not acceptable. So I will show the final slide. 1 minute. So this is a setup we developed at NIT Warangal. So this is the GTA welding equipment. We know that this is a tungsten electrode. So along with this electrode, we will supply shielding gas, argon gas. So in this nozzle, we will also supply shielding gas. In addition to torch gas, we will supply trailing gas. The additional gas we are supplying with this, and also we are also supplying from the back side of the weld also, that is called backing gas, so that we can avoid the contamination and you will get the good high quality weld. So before welding, generally we'll do HF and HNO3 acid pickling, and these are the welding parameters we use it for TIG welding. So with this, I will stop here. If you have any questions, you can ask.
Yeah, thank you, Kishore Babu garu, for the excellent presentation. I now request the audience participants, if you have any questions, now you can interact with the resource person. Any questions?
No, sir.
Participants? Yes, sir. Please go ahead, sir. Sir, any questions? Somebody was trying to speak.
Any questions?
Any questions? I think no one is ready to ask any questions, sir.
Okay, sir.
Anyway, thank you, sir. Thank you so much for your session. Participants, I'll be sharing the feedback link here in this particular chat and as well as in the WhatsApp group. So please fill that feedback. Thank you, Kishore Babu Garu.
No, thanks, sir.
Thank you, sir. Thank you.
Okay.
So another announcement is that the afternoon session will start exactly at 2 p.m. And the link I'll be sharing in the WhatsApp group. This is not the link, same link, but that is a different link. Please note that. So by 1:45, that link will be active. You can start joining by the time speaker starts the session at 2. So I'm sharing this link in the WhatsApp group also. So you can actually give the feedback for that. Thank you. Thank you so much for joining the inaugural session as well as the first session. Thank you all.